Hey, good to see everybody. Can everyone hear and see me right now? How are we doing on the seeing Brian and hearing Brian front? If you can't, just say hey in the chat if you can hear and see me. We're 1 minute early, but we got a lot of slides. So great job. Got a lot of questions on the homework. It looks like there might be an issue with the training. I know Christian emailed me about it. It looks like there might be a small issue that the sanity check's not working. I'm sorry, they're sometimes insanity checks. Haha, jokes. But and so good to see everyone, Nicholas and John and Allie and Kyle and Aaron and Zach and David. So thank you for being here. We've got 20 people here right now. So where's the other half of the class? Oh, they might be watching in the future. Good job if you're watching in the future. But the biggest thing that we need to do, hey Andrew, hey Leah. So let's go ahead and add Leah as a mod right here. If you're not a mod, we like making every mod. Mason, good to see you, Mason. We've got people joining in. Perfect. It is 12:40 right now. So the biggest thing is that be here, be asking questions, be interacting with the class. I know a lot of people, what was the mean of the test? The mean of the test, I think, was an 83. I'll double check. And so for the people who took it very late, I will be grading them very soon. So the mean of the test is an 83, I believe. Check your scores. They are posted, and we will try to get them back from VU, and we'll try to get them around and let you guys see what you got. So very sorry for the delays and all the grading. We are doing the Stat 201 test right now, and that is a lot of fun. But we'll also, some updates on that front. Your guys' coding night will be a take-home final. Please do not cheat on it. We did have an incident about 2 years ago where people started posting things online, and there was GroupMe talk. And the thing is there was like 8 people involved in it. And like, obviously no names here, but there was like 8 people involved, and finally someone was like, yeah, and they gave everything away. They were like, yeah, this is all that happened. And we kind of knew because there was some obvious stuff with the coding that it was like, and it was all connected. And finally, when the one person gave in, of course, it was, everyone else was completely, they were like, oh yeah, here's everything. Here's all the messages. Here's everything. So just don't do it. That's my biggest thing. It's no fun to deal with. Just don't make Brian's life not fun. So that's the theme of it. The final will be through Respondus. I'm gonna have a meeting with Dr. Hilafu and Dr. Liu here this weekend or Friday or Monday or something. We're planning a meeting and we're gonna talk about the final. So it'll be mostly multiple choice and true false and numeric entry. So here's the biggest thing. Knowing the concepts we're about to cover is so huge. You have to know the concepts. You have to understand them and to be able to answer, like the questions I'll ask in office hours. I'll be like, when would we use K nearest neighbors? And you have to be like, okay, well, what is K nearest neighbors? It's when things are voting. And we're gonna do it on the new material, but I'm using something we already know. Like, when would we use tree-based models? Can we use a tree-based model for a quantitative Y? Can we use a tree-based model for a quantitative Y? First 100,000 point question of the day. This is something we haven't talked about yet, but it is kind of a review question from 201 and 320. Can we use a tree-based model for a quantitative Y? Who knows for 100,000 points in the chat? Who's got that answer right there? Joe, I'm giving you 50,000 points. The answer is yes. The answer is yes. Tyler was the first one to say yes. The answer is yes. I'll show you right here. Don't worry. This is a new question. And there you go right there. There is a quantitative Y right there in the tree-based model. Can we use a tree-based model for a categorical Y? There's a categorical Y right there. And don't worry, when you get an answer wrong, I'm throwing all the people who answered 100,000 points. When you get an answer wrong, you remember it. You're like, wait a minute. We can use tree-based models for categorical or quantitative Ys. We've got here this is what we were kind of talking about last class. We were talking about logistic regression. So just to do a note from last class, logistic regression we use mainly for 2-class kind of identification. And so we're going to use a logistic model for that, but we could use a tree-based model. It's literally like statistics is like a toolbox, and you have so many options. You could use your multi-tool, you could use your screwdriver, you could use your hammer. Now things work better if I'm like, here's a nail, and you're like, I'm going to use a screwdriver and just pound the nail with the back of the screwdriver. Yeah, it'll probably work, but it's not efficient. So statistics is about trying out different tools, and a lot of times some tools might work better than others. So if you have a categorical model, I want someone to say, this is a review question now for another 100,000 points. Keep answering these questions. What is this measuring actually since it's categorical? It's making predictions on the categorical Y. I'll start up some real structured going through the notes here. So it's just a model that is going to make predictions on a categorical Y? And what are two models we know right now? Or you can mention a lot of different models. What are some models that would make predictions on categorical Ys? 100,000 each model, someone puts in the chat, that would make prediction on the categorical Ys. And these are great examples of what we could put on Respondus. So like we could be like, select all the models that can be used to make predictions. Logistic, boom, 100,000 right there. Definitely logistic, we just covered that. What else? Everyone's saying logistic. Yep. That's the key point of logistic. You're right. Here we'll start. Any other ideas? I mentioned one of them earlier. I mentioned it a little bit earlier. What are some other ones for 100,000? Other models that can be used to make predictions on categorical data, on categorical Ys. That's what you would predict. You predict a Y variable. Any other ideas? What's the name of today? And then I mentioned one other model where things vote, like nearest things to them vote. Any ideas in the chat? 100,000 points. We need at least one more. Well, forecasting is just the idea of making predictions. I'll still throw 100,000 right there. Tree-based models, yep. Partition models are tree-based models, yep. That's the theme of today. And Spencer got the nearest neighbors, yep. Vanilla partition is meant like kind of like simple partition. Ooh, everyone's saying K nearest neighbors now. Hopefully, am I on the ultra low delay settings? Yes, I'm on ultra low. It just seems like, just want to make sure everyone said K nearest neighbor in that moment. You are correct. K nearest neighbor is, you can have it vote on quantitative values or numeric values. And we have tree-based models, which are partition models, which are the same thing as vanilla partition. So does everyone hear that right here, that these all mean the same thing? Tree-based models, partition models, decision trees, sometimes they're called regression trees if they're quantitative. They're all kind of synonymous words. So when you learned in 201 decision trees, you were doing partition models. And then we specifically call the ones that are quantitative, sometimes we call them regression trees or stuff like that. So there are kind of specific names, but they're all partition models, tree-based models. Multinomial would be a multiple level categorical Y variable. So you'd use multinomial logistic for things like a categorical Y with 3 levels. So you could predict like left, right, or straight, like which way will a car go at an intersection, left, right, or straight, and you could use a multinomial logistic model. Great job, Kyle, 100,000. We'll turn down the points here now, but great answers in the chat. Keep them coming, keep interacting. Okay, so what do we see right here? A partition model, widely known as the decision tree, makes predictions via a set of rules. So all we're going to do is make rules. Like if the first week's sales are greater than 60, a product is type B. I have to sneeze, 2 seconds here. I sneezed into my arm, so no one come after my arm. Don't worry, I am totally fine right now. At least I think so. I don't go outside much. So if the first week's sales, thank you, Aaron. If the first week's sales are greater than 60, if it's type B, if it's summer, then classify as a success. So you guys are awesome in the chat. So all we're doing right here is making rules based on the X's. So you see here, we're predicting if something is a success or failure. And then at the end here, what are we doing? We're changing it to predicting if something is quantitative. I think you have to sometimes realize that there's concepts within the slides that people don't notice. Like here, we're predicting a categorical Y. Categorical Y again, we're just predicting the other 2 level of it. And then here we're predicting a quantitative Y. So we can make many different types of predictions from this, categorical or quantitative. So remember that right there. Tree-based models can be used to make categorical or quantitative predictions. This is a non-parametric model, which means we're not using like a linear model, not using a logistic. It's just based on rules. There's very few assumptions with these, which is super awesome. It's just like, you just make rules. You say, if this happens, this happens. So it's really easy to make these models. They have very few to no assumptions. You just make rules. Here's a model right here. Here's what it looks like. If you notice, we're just dividing the data up. In this region right here, 100,000 points, first person to answer. What would you predict a new point in this data would be? What would you predict a new point in this region would be? Any ideas? What would you predict? In this region, due to the majority level of it, what would you predict? Who's got it for 100,000? Pay attention, be answering all the questions. David got it right there. Black square, you are right. How about over here? Now, this is a tricky one. I'm going to have to zoom. I'm going to have to look at this. What would you predict in this region? Who knows this region right here? Let's see. We'll get the first person answer now. Who knows this region right here? Open circle. Aaron got it right for 100,000 right there. You are correct. That would be an open circle right there because it's the majority level. So if you notice, Julio, I love it, Julio. It's so good to see you here. It would be an open circle because that's the majority level. This is tree-based models. It's decision trees, and you're about to hear it at a higher level here than we do it in 201. So you can see here the new individuals right here would be classified as a square or as a circle, and we're just going to use the majority levels, the majority rules. That's what happens in statistics. It's like, I mean, imagine if you're at a party and they're like, okay, we're going to order ice cream. Should we get chocolate or should we get vanilla? And I'll show you guys something super cool. I don't know if we did it last time here, but how can I go to Streamlabs? Streamlabs. No, wait, am I not logged into Streamlabs? Okay, maybe not. I can do voting on stuff. Maybe we'll try to do it. Log in via YouTube. We'll see if it logs in. So, and am I logged into the right thing? Which is like destroy everything. I don't know why it logged me out. But we can do voting now on stuff, so we could actually take votes. A lot of fun. Good stuff. Oh, we did that last time, I think. So you guys have probably seen it. So we can still use decision trees for quantitative models. Now with quantitative models, we would use the mean of all the values. So here's the small shift. Remember, in categorical models, we use the majority level of a partition. In quantitative models, we use the mean of that partition. So we want to use the mean of the partition, which is just all the values in that partition averaged together. So the mean of the partition is what we would use. Does everyone understand these concepts? Please slow me down. All the math is just shown here, but we don't do this by hand. You won't ever really solve a problem like this by hand. I mean, I guess we could put a theory thing on the test now, but if you just understand conceptually what's going on right here, that this blue star would be predicted to be the mean of everything in its partition, and the green would be the mean of everything in its partition. That's all that's going on. The blue star here would be the majority level of its partition, and the green star would be the majority level of its partition. Great job, great answers in the chat. So we've got rules like this, but this is not usually how we do it. We don't usually make some kind of non-linear rules. We're about to show, I think, some better rules right here. Sorry, hiccups. The rules we usually get are just usually things like greater than or less than a certain value. There's infinite ways to make rules. You could be like, if it's a Tuesday, predict this. And so you can make rules based on categorical levels, quantitative levels, anything you want. And so we get all of this right here. So let's look at how we actually make the rules. We actually make the rules usually based on greater than or less than a value, or we usually make it based on certain levels. Like, is it in group A, B, C, D, A, B, C, D, E, all those right there. We make it, is it less than 5? Is it greater than 7? Is it between these values? And you can see this visually going on. There's the visual of what we actually do. Let me explain. This would be such an easy way to make two non-linear rules. So if you look at this right here, you'd say, well, everything is perfectly divided up. We have all the red in one spot, all the blue in another spot, all the red in another spot. This is a perfect partition. Everything is perfectly classified. I'm gonna grab a glass of water, and I want everyone to put in the chat what the R squared is. You get 100,000 points if you can tell me what the R squared is of this decision tree right here. No one knows what the R squared is? John got it. John got what the R squared is. It's 1. Why is the R squared 1? Because 100% of the variation, and make sure to hit the live button below. So, got Zelda glass right now. Make sure to hit the live button below everything to make sure you're watching live. 100% of the variation in the points is explained by the partition model. Does that make sense right there? 100% of the variation in the points is explained by the partition model. It perfectly divides everything up, and that's what an R squared of 1 means, is that everything is properly classified, as in there's no variation left unexplained. We always need to think back to what these topics actually mean and be like, what does it mean to have an R squared of 1? Well, everything is perfectly classified into the right group, so we're doing excellently well on that. Here is the same model being created, well, not the exact same, but being regardless of direction, the points, clarify that, Kyle. I don't understand the direction of the points. We have here red points and blue points. And if you notice, this partition is all blue. This partition is all red. This partition is all red. And then here's a tree-based model using just linear cuts, because this is just horizontal and vertical cuts on one variable. So this is only using one variable cuts, like x below this, or yeah, that'd be x2 below this, x1 greater than or less than this. It just depends on how we're writing. The cuts are linear, but the rule isn't. Yeah, exactly. The rule is, well, it's two variable rule. It's an equation based on it. So this is like an equation of a line rule, but these are just horizontal and vertical lines, which only take into account one variable. So the idea here is, well, we could make really complex rules, but can't we just do the same thing using linear cuts? So this is how we often make the rules, is based on one variable. There are complex ways of doing it, but if you look here, it didn't take too many rules to make the exact same model that has the exact same r squared. It's not the exact same model, but it's got the same kind of r squared. Everything here is perfectly classified. If you look, all blue, all blue, all blue, all red, all red, all red. So sounds like I'm saying all right, all right, all right. But that's what we have going on right here, is we can make these rules that are we usually use just linear rules. It's the way we do it in kind of simple partition models. And we could do a model like this just using linear rules. So let's use those linear rules. How about this model right here? Oh, man. This model, I'll throw a million points if anyone knows what model to use for this. There is a model. This is in later notes too. No one's going to know. I'm going to give it 10 seconds. If you knew, you would blow my mind. But this type of data right here, the way it's configured, triple linear, I like that. I'll give you 100,000 points for that. It's actually, this type of data would require support vector machine. Support vector machine puts a hyperplane. It adds an extra dimension through it. And I don't think we show that here, but I want to pull up if I had it right handy right now, I'd show you. But we put an extra dimension. You see how that's flat? With the third dimension, it would rise up. We use a kernel to find the third dimension that properly separates it. And then you put a hyperplane through it. So if you imagine, it's going to make it rise up by adding a third dimension to it. And all of a sudden, it's like a button, and you cut through it, and you insert that hyperplane that does classification. And so that is support vector machine, which we have not covered yet, which can obviously be used for categorical data and quantitative too. But there's so many things. And if I see this, I know it's support vector machine. Yeah, it just bends space and time. It adds an extra dimension and inserts a hyperplane to do separation between. It's insanity. The people who thought this stuff up, I'm like, how did you think up these things? So when I see that, I know that's a support vector machine pattern. That would be the right tool to use. But you could do it for this probably. Yeah, they would have a lot of trouble with this. Like I was saying, you could do it, but there's better methods. So we've got here a bunch of rules. Let's take a look at the rules. Once again, I don't always read every slide because I'm going to show you the example right here, which is basically showing you what's going on. We have right here that we're just doing above a certain value. Here's rule 1. Then we add in rule 2. Then we add in rule 3. Then we add in rule 4. Do you see how each time we're dividing up the space more and more and more? We just have rule 1, cuts it like this. Rule 2 cuts it again within rule 1. Rule 3 cuts within the new cut right here, and then rule 4 cuts here. Now we could have another rule that cuts over here. It's just going to cut within each rule. It's basically, I kind of amount it to taking a ball of clay and separating the ball of clay smaller and smaller. In class, I can't do my in-class examples anymore. I'll be like, John, here's a ball of clay. I'm going to hand you half the ball of clay, and you'll take half the ball. And they'll be like, okay, now hand Aaron half the ball of clay. And then Caleb's next to you, John. So I'd be like, okay, hand Caleb. Oh, man, don't you miss being in class? We're here right now, but so you would keep handing it, and everyone's breaking it apart smaller and smaller. In this first one right here, this is where I hand John the ball of clay. Now, he didn't take half of it. He took like a quarter of it. Will each rule be a thinner and thinner line? No, it's just the way it's graphic. Great question, Zach. It's just the way it's graphically being shown right here, so you can kind of see which rule. The first rule has the thickest line. It's just kind of showing you visually which rule is which, so you can kind of track by the end, like first rule, second rule, third rule, fourth rule, just so you can track it right there. Great question. 100,000 points, Zach. But that's just a visual cue. Here is just some more rules being made. Once again, we're just covering how rules are being used. We just partition our data. We say x greater than 1 and x less and x2 greater than 0.6. So x greater than 0.5, that's going to go this way. And x greater than 0.6, x2, that's going to be this. This region right here, or this, is this region right here. These are just rules. Once again, the key concept is we're just going to take an x variable, and I want someone to come up with a rule right now. 100,000 points each rules. I know I'm throwing crazy points today, but I want you to come up with a rule, and I want you to make it actual data. I'll give you a hint. Here's my rule. If somebody has a height greater than 68 inches, then male. That is my rule. That is my rule. I didn't write out the full tree, but if you notice, I'm going to use it to make a prediction. I'm going to say, and you don't have to use quantitative. You could say, if somebody, I'm just trying to think of like, if somebody, I can't think, if somebody, but that's quantitative. If somebody got an A on take home, if somebody gets an A on take home, they get an A on in class or something like that. So if someone weighs more than 150, there we go. If someone has a weight greater than 185, then male. Yeah, so great job, Saeed and Caleb. 100,000 points right there. Caleb, good to see you in the chat. So those are rules making predictions. Both of those are predicting categoricals like this model is, and both of those are using quantitative. If someone studies more than 10 hours, they're getting an A. I think I was thinking of that one. I literally think I thought of that, Will. 100,000 points rule. If someone has an A in the class, GPA over 3.5, let me think right here. So Joe, great answer, 100,000 points. It would be, you would predict for, actually you can do that. Joe, I stand corrected, because now in the Y variable, Joe, you'd only be predicting two things right there. You'd be predicting someone has a GPA above 3.5 or someone has a GPA at or below 3.5, or however you want to classify it, 3.5 and above, below 3.5, but you're doing a categorical X right there. So probably you might want to use that model to predict someone's actual GPA. So you might say if someone has an A in the class, you would classify them as a GPA of 3.8. And that goes back to some of the earlier notes. Yeah, there you go. I like it right there. Goes back to the earlier notes right here, that when you do quantitative models, like usually when you make a quantitative prediction, you will predict the mean of that group. So if someone has an A in the class, you will predict the mean of that group. So whatever group they're in, you would say, well, then if someone has A in the class, their GPA is expected to be this. Like that is your prediction. So when you do quantitative numbers, you can turn it into a categorical though, but I would probably keep it as quantitative. So that's why I corrected myself when I was reading the answer. I was like, well, actually you can do that, but I might keep it as quantitative because there's more information in quantitative. But maybe you're looking at like below a 2.0, which is that academic probation. So maybe that might be an interesting value. So then you might predict when are people going to go on academic probation and stuff like that. That is really great. Here's what the tree looks like visually. And so I hope Julio's still here. He's probably seen this, is that I wish, and I can't mark on these as well, but we just follow down the tree. Can I do that? Oh, I can almost do it. You can see we just go down the tree. You're welcome, Joe. Thank you so much. You just follow down the tree and you say, okay, they've got an X less than or equal to, X1 less than or equal to 0.5. Then you follow down this way and you say, okay, they've got an X2 less than or equal to 0.4. Then we go here and we'd predict a dot because 19 of the observations are a dot. And that's all we do. Once again, please take this note. In a decision tree, the leaves make the prediction. These are the leaves. These are all the leaves right here, the things at the very bottom. If this is an upside down tree, the leaves are at the very bottom. So with all the leaves making predictions, in categorical trees, the majority level is predicted. In quantitative trees, the average of the leaf is predicted. So once again, as sirens go outside, I don't know if you guys can hear that. In quantitative trees, doing reverse, the average of the leaf is predicted. In categorical trees, the majority level is predicted. So if there was a new observation right here, then we would predict the majority level for it. So anything that's a new observation right there would be predicted to be a white triangle, where anything over here would be predicted to be a black dot. We predict the majority level when it's categorical, and when it's quantitative, we predict the average. Now, please, please, please keep coming to class, and please keep taking notes on this, because your final is going to be very conceptual. Very, 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 very conceptual. So all these notes I'm saying, we're going to try to put as many of them on there where it's like, when a decision tree makes a prediction, or when a prediction model makes a prediction for a quantitative variable, it will use the naive model, the majority level, the average of, and it's quantitative, so it's going to use the average. So there we go. And we'll try to put tricky things on there, not to be too tricky, but you want to make an answer that sounds right, that, you know, people won't be tricked by if they know the concept though. Here's all the rules. This video will be posted. Yep, every one of these videos is posted after, so you can always rewind. And if anyone ever puts in timestamps, I'll throw 100,000 points for each timestamp. So I love timestamps, and it helps out a lot of people. People will notice, like, here's where Brian reviews this. And a lot of people really like the timestamps. So thank you, everyone. Put comments on the videos. Put notes on the videos. I'm also putting, you can only get one of these, 100,000 points for each note you want to put on the video. So put notes below the lectures is a huge help. Students always love that when someone writes a note. Like when you're studying, put a note below the video. So it's not in the comments right now, but after the video posts, you can post a comment below the video, and that's a huge help. There's all the rules. Here's the terminology I was just going over. We call these branches right here. They go through nodes, and then most importantly at the bottom we have leaves. Just think of it as an upside down tree. Just you got your tree, and then you flip it upside down. That's all that's going on right here. It's just an upside down tree. So you see that branch going out, and then the branch has like a node in it, like a notch, and just a node right there, and then the leaf at the end of it. It's a weird looking tree. It's just kind of flooding everywhere. But you have to make sure you can think of this with the concepts we already know. The very start of it's kind of the base of the root of the tree. You got your branches going out. They hit like nodes where they just go through a little like nodule in the tree, and then you got the leaves at the very end of the tree. Does this all make sense? This is like the easy, fun part of the lecture. Hopefully no one's like, oh my gosh, this is impossible, because this is the easy part, I believe. Everyone doing all right? I miss you guys. I miss seeing everybody. I imagine everyone's taking great notes right now. So that's why I'm like, yes, keep taking those notes. Okay, let's continue on here. You think so? I like that. I like that, John. So we have right here everything I've been saying repeatedly. If you guys know my teaching style, it's to repeat the big concepts multiple times. So the probability of being in each class equals the proportion of individuals in the training set in that partition. The majority class dictates the classification. Literally, the majority level of a leaf is what we predict. I can't highlight just that. I wish I could. But the majority level of a leaf is how we make the prediction. The predicted Y value is the average among all the individuals in that leaf. Literally what we've been saying. We've done this multiple times now. We should know that when we get to the leaf makes the prediction, and we have rules that go down to it. So we can see right here that there's all of these rules that we would go through, literally right here. Then when we get down to the leaf, it makes the prediction. Great stuff right there. We've got the way we split it. If the answer is yes, then we go to the left, and we'll see this here in a moment. If the answer is no, then you go to the right, and we'll see this, I think, here we are. Boom. Might have to zoom. Can everyone see this clearly? Tell me zoom in or not. But what we have right here is we have loyalty days less than 357. And so if they answer yes, it's hard to see. It's right. I'm looking at this right here. Can't highlight it. Wish I could highlight on this. Well, there we go. We're looking at that right there. It's legible but small. We'll zoom in on it. There we go. Feel free to ask me to zoom. The cell looks way better. So we have here that if someone's loyalty days are less than 357, we have to ask ourselves that question. Is someone's loyalty days less than 357? And if we say yes, we'd go over here and we would predict no. And I like the way this looks because, oh, if I can have, it's so hard to highlight just the thing I want. It's not going to do it. Ain't going to do it. So we would not predict yes. We would predict no because no is the majority level. And you can go through this tree in any way you want. you can go down and say, okay, they have loyalty days. Are they less than 357? No, which means they might have 380 loyalty days. What is their lapse? If their lapse, and you have to be careful now, if their lapse is 8 min, then you have to go to the left, because remember, left is yes. So now we go down here and we say, is their loyalty day less than 601? And we'd say yes, and we would predict no again. Can I highlight just no? It's very hard to highlight just no. Well, we'd choose no. So remember, the tree shows you which way you'll answer the questions. If you answer yes to any of the questions, like are loyalty days less than 357 for the customer, then you go to the left. Are they in the group 8 min or VRL? If you answer yes, you go to the left. Now you could get to the end and they could have a loyalty days of 800, and then you'd go over here and you'd actually predict yes, because yes is the majority level for the 29 individuals in that leaf. So let's go right here and we'll continue. I was going to ask a big question, but it would take up too much time. If you want to see how many people are in the tree total, you can add up these numbers right here. I think it might be a question. Will the yes and no alls be shown on yeah, we should show it. You shouldn't have to assume it. Great question, David. 100,000 points. Keep those questions coming. We should show it to you. So always make sure to ask the question. I think a lot of people go through it too quickly. Ask yourself if someone's loyalty days are less than 355. And if you say yes to that, like they have 200, you'd go to the left. So no, they have like 400, you'd go to the right. So always be very careful. I'll just see people do it too quickly. I've done it too quickly, and then you get it wrong because you're like, oops, I misread the problem. I do it all the time. So let's see here. The tree naturally, oh yes, I love it. This is a huge note. So would you start with information like loyalty days? Yeah. You'd look in, Saeed, great question, and I think we might have another one. Yeah, I'll publish these longer ones right here. I'm sorry, I noticed this right before. Let me publish them now. I noticed this right before class, and I saw some key things. Let me do that, Clay. Clay, 100,000 points, and Saeed also. I dropped my pen. Give me 2 seconds. I'm going to post these here. I appreciate that. I noticed this. It was literally, if you notice, I was saying hey in chat, and then I went, and I was looking through the notes, and I was like, there's things I want in this. Okay, cool. Add item. It's just, I've always liked the longer notes. I mean, I want every bit of information being presented. It's like a book. It's not, okay. Tree-based, all slides. Okay, cool. Okay. You should see it now. If we make this an R, would it be just making a lot of subsets? You won't have to make the subsets. It'll do it for you. There you go. Everyone's very happy. So in R will do this for you, and tree-based models incorporate all the interactions. Tree-based models are awesome because you can look at someone, like if you're looking at how people perform in school, you can look at how their attendance interacts with their assignments performance, interacts with their quiz average, interacts with their test average, and maybe if they'll pass the class. So it can go within each variable, and it naturally incorporates all of this. So tree-based models, huge note right here. Like this can lead to so many true-false questions and everything. Like I can think of true-false questions right here. Like you must make sure for tree-based models that you incorporate interactions for them. The answer would be false. Tree-based models naturally incorporate interactions. So you don't have to take an extra step with tree-based models, or you have to. It's weird because I don't want someone to think we're saying ignore them, but you have to watch with the wording. Like maybe this is a good true-false. Tree-based models cannot handle interactions. True or false? Tree-based models cannot handle interactions. Tree-based models cannot handle interactions. Or tree-based models do not handle interactions or do not use interactions. That is so false. That is so false. I'm going to try to put as many of these things I remember on there when I'm making the test. That is as false can get. Tree-based models naturally incorporate interactions. They're the direct opposite of can't handle it. They're like the king of interactions, the queen of interactions, the ruler of interactions. They're the Cersei Lannister of interactions. I don't know. Was she good? So, she wasn't the worst in the show at the very... Well, I don't know. It's up for debate. We won't talk Game of Thrones Season 8. That never happened. They're gonna remake it. It'll be... I don't know. We've got right here how to make predictions. So we've got right here. Imagine a product, the success of a product launch. It's product type B. You noticed here, and we will include this on your test. We won't assume that you know yes is to the left. It ended at season 6. I'll take that. We will assume left is to the yes. Now, we know that because we've already done one. Once again, if we put it on the test, we're going to show that to you. You don't have to memorize yeses on the left. It's just how this tree works. You notice here that the amount sold during week 1, the number of units sold was 4. So we have here that it was greater than that. We also have here that's product B. And then we go down here. The product sold was greater than 3.2. So the product's going to be a success. Yeah, because there are 75% successes in that group. And we predict the majority level. Now, what is switching? Someone for 100,000 points. This tree was predicting a blank blank, where this tree is predicting a blank blank. Be thinking about that because it's a key concept. Yep, you follow the path down till at the end. Great answer, Saeed, in the chat for 100,000. Throwing big 100,000 points. Please keep coming, class. I can't state that enough. I think anyone who does poorly is not going to be following along and be like, I'll just watch it. I know people can watch it after. I know people's lives are busy, and I know the world is crazy right now. But if you can come to class and if you can watch this live and interact, please do it, because I'm going to ask you guys tons of questions. And the more you write in the chat and the more you take notes while watching live, I promise the better you'll do, because we're going to, yep. Ali, 100,000 points. Great answer in the chat. You said it was first or last one was a predicting a categorical, success, not success. And this one is going to predict a quantitative. We're predicting the birth weight of a baby. We've got the baby was born at 40 weeks and the mother is 5 feet tall. Don't know why how tall a mother is would matter. Do you notice something? 5 feet tall is not in the tree. We just need to know that the baby was born at 40 weeks. So is the gestation period, and are they a smoking mother? Okay. So gestation period, oh my gosh. Can I highlight just that, please? Yes, there we go. Then we go here. Is it less than 40? No. We go here. And is she smoking now? The answer is yes. Yes is to the left. And so we should get this right here. If I could highlight it, that'd be nice. I'm not going to highlight it. The answer is 3,420. So if you notice the way I'm following the tree, yes is to the left. And so just making sure I did it correct. Remember, she has 40 weeks. 40 is not less than 40. So we go to the right because 40 is not less than 40. If anyone's confused on that, when I was at this spot in the tree, 40 is not less than 40. So the answer there is no, and no is to the right. Is she smoking now? Yes. Yes is to the left. How do I know that? At the very top of the tree, what I'm currently highlighting right now says yes is to the left. You have to ask yourself the question. When you get right here, you have to say, is she smoking right now? That's the magnify button. So what does the 3,004? That is the birth weight of her baby in grams, I believe. So that is the birth weight, Nolan, right there. 100,000 points, Nolan. Making a mod on the channel, Nolan. That is the birth weight of the baby in grams, because we're going to make a prediction. And let's see here, 3,042 grams to pounds. That is 7.5 pounds. I know, right? You're like, man, these are humongous babies. These are like Game of Thrones, that dude who like bust, like, what was that guy who like, they had those giants. Man, there was so many cool things we could have learned about. I'm going to stay happy and not think about it. So many cool things could have... So many cool stories. The mountain. Sad. I know, right? What happened to him? Like, literally, what happened to him? I don't understand. I dude who played him. Man. Okay. Huge strength. The interactions. Interactions are often difficult to put in, but once again, partition models naturally incorporate interactions. This is probably why we reduce the slide sometimes. But we have here, once again, I can't state this but a billion times. It's gonna hurt me when someone's like, tree-based models can't do interactions. No, that's like their superpower. They completely do interactions every which way they need them. They can sort through the variables and find them very easily. Tree-based models are awesome at interactions. Amazing. So here you see some interactions. I'm not going to focus on this too long. It's a review of interactions, just showing you how things work. And I think we might have covered this in class already. Please note how this works. We'll look at my favorite version of it. It's the one on the right. So if you notice here, don't worry, this won't be a major topic on the test, but what's an interaction? It's the impact of one variable on y depends on another. So the impact of someone's experience on their salary, do you see the impact of X on Y depends on someone's education? Listen again here. The impact of somebody's experience on their salary depends on education. When education is large, experience has a negative coefficient. When education is small, experience has a positive coefficient. So the impact of experience on salary depends on someone's education. Same thing over here, but I like the one that goes from positive to negative because that's a more drastic, easier to understand interaction where it's like, oh, you have very, let me, it's even hard for me to see. It's like, oh, you have a very high education. Well, then your experience might actually lower your salary. I always talk about people who maybe have a PhD in computer science but got it 50 years ago. Well, someone who's a new PhD in computer science might have a higher salary, and they'd be over here. This would be the new PhD in computer science, and this right here on the very end of it would be the old PhD, 30 years of experience in computer science. So you might hire the person with the new PhD for more money. But then if you had someone who did like carpentry, and we're calling education like formal, like school education, I definitely know you can be educated in carpentry. Don't worry, like that is a very good skill to have. So if you had someone who we think about carpentry is not really a school, go to college type thing. It's a trade school type thing, which very important still. But you would have person A who has zero experience, who has a carpentry degree. And then you have person B who has 30 years of experience in carpentry. And it's like, whoa, you have 30 years in carpentry. We are totally going to hire you because you are very experienced. It's weird because the other person who maybe has more experience and the degree is older, the degree is less useful. So how does experience impact your salary? Well, it depends on what education you have. What does the p-value mean? You can use it in context. Yeah, and we won't focus too much on p-values. Great question. 100,000 points. I have you right there. The p-value right here tells us if the kind of changes in the slopes we're seeing, this would be a p-value of 1 because this is, if you can't see, these are parallel lines. This right here, these differences in slopes are super likely due to what? Another 100,000 points. The differences we see between these slopes, which is nothing, and the p-value is 1, these are parallel lines I'm making. The differences between those are super probably just due to random chance. Will, right there, you're right, 100,000 points on Kyle. So, and Aaron, you guys know my random chance thing because if the lines are parallel, they don't have any difference, and any difference we observe, which is nothing, it's probably just random chance. Now, these lines right here have a pretty large difference, which is unlikely due to random chance. Unlikely due to random chance. And I think we're going to do Twitch either Thursday or Tuesday. And if I'm allowed, I might see if Julio wants to do an interview. Like we do our first stream on Twitch and we interview Julio again. And so that would be a lot of fun. I'll see. I don't know. It's all up to him. But yeah, if you were saying, yeah, I don't know. So I'll put out announcements about, I'll be like, yeah, for fun, for quarantine, let's do an interview. And so that'd be really cool. And we'll talk stats and we'll talk everything. So I'm trying to get that planned up and trying to get everything worked out. Showing interaction, cool. We know what interactions are. Deals with interactions, cool. This is why some slides are eliminated. Okay, here we go to some more serious stuff. Let's get serious here. So we need some sort of measurement tool to see how our tree is doing. We would love it if our tree, exactly, people would love that. I think they, yeah, I'll talk to them. We could do it. Yeah, we were planning on doing another interview and we had talked about it because we had a lot of fun last time. So we have right here some metrics. Now I'm going to show you guys my favorite metrics. My favorite metrics are Gini Index and sums of squared error. Now, why do we need, like, I'll tell you this much, you can use entropy and sums of squared error, or you could use Gini Index and sums of squared error. Anyone have any idea? This is a theme of this lecture today. Why we probably need 2 of those and we can't just use 1 of those. And which one would be used for which and which one would be used for which? Any ideas on this 100,000 points? Who knows? This is the theme of the lecture, knowing what to use and when, which is going to be a huge thing on your test. Why would you use entropy? Why would you use Gini Index? Why would you use sums of squared error? Sums of squared error is used when? Oh, it actually says it on the end of it. Who knows? So when do you think Gini and who knows? Yeah, exactly. And more specifically, John, the accuracy, we don't really use accuracy right here. We use Gini Index. It's cat versus quant. Everyone's saying it right there. So entropy and Gini Index are used for categorical, and then sums of squared errors used for numeric quantitative predictions. So very important right there. Cat versus quant, 100%. Everyone knows what's going on. This is what we have. We have all of this right here. So we have all of this right here. How are we going to pick the right rule? We need to keep splitting the tree, and we're going to see how well the tree is doing. So we're going to expand the tree often to a maximum level. So we can take a look at how this is done, and we can look at the impurity. So what we want, our goal, is that these leaves are 100% pure. Now, you could do that by putting each thing into its own leaf. And we'll talk more about that towards the end of the lecture, because there's a technique where you can kind of do that, and actually do it correctly. But this is kind of like where you do k nearest neighbor of 1, and everyone gets to vote on themselves, and you probably have a model that's what for 100,000 points. If you were to split the tree as far as it went, you'd probably have a model. This is so key. You'd probably have a model that is what? And I wish we could just do fill in the blank, but those are often hard to put and get right answers on. Like we could do a word search. Maybe we'll do that. Maybe we'll give a bunch of terms, and then you'll have to be like, we could give like 20 terms. Basically, it's like, here's possible answers, and we could ask like 8 questions. It'd be 100% accurate. It would have an R squared 100%. Joe, or Caleb, right? Caleb, you are right. It would have an R squared 100%. It would definitely, well, not definitely, most likely be this. Most likely be overfit. It'd most likely be overfit. Because if you split the tree down into just one observation, well, then it's always going to be perfect. John is right. It's going to be overfit. Probably. I mean, we can't say we know it's overfit, but it's a high candidate for overfitting. Just because it's so accurate, it's probably not going to work on new data, which is the definition of overfitting. You can see right here the partitions being made. Now, what we want here is we want to get where everything is exactly on the mean. So what would be great is if we were predicting people's ages, what would be a good version? In version A, a leaf has people who are 19, 20, and 21. And version C, the leaf has everyone who's 20 in it. So what would be the better? Leaf A, people in the leaf are 19, 20, and 21. And version B of the leaf, people are all 20 in the leaf. What would be better, leaf A or leaf B? Remember, leaf A is people are 19, 20, and 21 in that leaf. And so if there's just 3 people, we'd predict 20. We'd get person wrong by 1, person 19 wrong by 1, person 21 wrong by 1, person 20 perfect. But in leaf B, everyone's 20. So what would the sums of squared error of that leaf be? Well, if everyone's 20, then everyone's perfectly predicted. Well, you're right, 100,000 points. Everyone would be perfectly predicted by leaf B, and the sums of squared error would be 0 for leaf B because there is no error. We'd have a perfect prediction. Joel, the 100,000 points too, and Aaron and David. Great job. Keep following along, and you guys are doing excellent. So we want to get everyone to be the same quantitative Y values in here. So you see right here, entropy. I do not want us calculating entropy on the test. Entropy has a lot of, I don't talk about it that much. I just don't use it much in my statistics toolbox. Entropy is one way to measure the impurity of a partition. What is impurity? Tell me, which of these right here looks more impure, the left or the right? The answer is the left, because it has more kind of dots of different colors. 100,000 points, Aaron, and everyone right there. Yes, you are correct. The left looks more impure. The right is more pure. And our goal is to get purity here, so we do not want high entropy. I'm not a big fan of calculating it just because the computer does it for you. You just need to know that entropy is impurity. Take a look. In right here, this partition right here, you've got, I'll just highlight it. You've got 27 out of 30 conform to group A. 2 out of 30 conform to group B. And my mouse is being all crazy like. 2 out of 30 conform to group B, and 1 out of 30 conform to group C. So the entropy right here is 0.56. So with this right here, you'll notice that we actually have a lower entropy than the top one, where with the top entropy, take a look, you've got 1/3, 1/3, because I think it's 10, 10, 10, 1/3, 1/3. So you've got all this 1/3 right here, and that's a very high entropy. So you want a lower entropy. Smaller values of entropy are better, with 0 being the smallest possible value. What would 0 mean for R squared? If entropy was 0, then the impurity is what? And then R squared would be what? Oh, that's a good theory question. If the entropy is 0, because it's a measure of impurity, what would the R squared be? If the entropy is 0, then the R squared must be this. 1. You're right, 100,000 points right there. And because it's impurity. If the impurity is 0, everything would be properly classified. Great job, Clay, 100,000 also. It would be, and everyone in the chat, Julia, nice job. So keep giving those answers. Now we get to Gini Index. I love it. Tool 1 will notice this in their output. They'll be like, what is that Gini Index? I'll be like, oh, don't worry about it. So a Gini Index of 0 means the partition is 100% pure. So once again, it's a measure of impurity right here. The proportion of individuals in the partition who belong to class I. So let's take a look at here. It's 1 minus this. We've got a bunch of calculations for you to take a look at. And there's a cool mathematical thing to this. When you're predicting group A, B, or C, you can take a look at right here. We've got 1 minus this. What's really interesting, and if I remember how it works, you will actually get that the highest Gini index you could possibly get is always going to be 1 minus, am I doing it correctly? 1 minus that value, because it's just a weird mathematical thing. I might write it out right here. Let's show it. I've shown it in class before. Okay. So the worst Gini index you can get is always 1 minus that value. Because, and let me make sure I got the math right on this. You got here 1 minus, and then you go right here. And I do it this way. And there we go. Okay. Now what does this represent? This represents the percent of individuals that conform to each class. As in group A, or in the first partition, we have here half and half. And in the other partition, we have half and half. And so when you do this mathematically right here, what do you get? You get 1 minus 1 half, and this equals 0.05. So this would equal 0.50. I misspoke right there, 0.50. But what am I getting at theoretically wise here? This is just a big theory thing, probably not the most important point, but I found it very interesting. Is if you have 4 groups and you have the worst impurity possible. So this is the worst impurity with 4 groups. So when you look at this right here, what does this solve to? With 4 groups with the worst impurity, you would actually get, so it's just 1 minus 1/4 is the worst impurity. So you'll notice higher levels of impurity are worse. What is the best level of impurity you can always get? Well, that would look like this, where you have it completely conformed right there. So inside of this partition, everything is all that one group, and then everything else would be 0/4. So the impurity right here would be 0. The impurity inside of this partition would be 0. That's a 2. And so this would be 100% pure. So this is a measure of impurity. So just take a moment and look at the mathematics here to notice that this equation would simply solve to 1 minus 1. So the worst you could get, we'll zoom out just a tiny bit here. This is the worst you could get. That is the absolute worst. And this is with 4 groups right here. And then the best you could possibly get, and so this would be the best. Space pen for the best. So what you want is you want values like this. You want things to be all in the one group, and then you want the zeros up here where you don't have it. But look how this is perfectly evenly split. This is the absolute worst, and this is the absolute best. So you see an example also on the slides. Great answers in the chat, 100,000 points. Thank you for all those answers. So I know we're throwing out crazy points. Keep track of them. You can just be like another 100,000, another 100,000, but you got to be here live. You got to be practicing. If you notice right here, the top example is one of the worst. Now this one isn't perfect, but we see down here that a partition has 27 members in class A, 2 members in class B, 1 member in class C. And so we have that, we would guess that people are class A, and it's a pretty low Gini index. So it's a pretty low Gini index value right there. And remember, this is not the wealth inequality index. I think that's another Gini index. But so you want Gini indexes close to 0. Very important. We could do true falses on that. Be like, Gini indexes close to 1 indicate that things are very pure. No, a high Gini index indicates impurity. So we see right here, We've got probability of misclassification. I might skip this right here. We've got one last, yep, well, it's just how to do it right here. Not that important of a slide. I know it's got a lot, but don't worry. So here we go. The sums of squared error. This is so key because this is for quantitative data. This is for quantitative data. When you do the sums of squared error, you will add together all the sums of squared errors for each one of the partitions. So I think I see. Can you explain what Gini Index means in context? Sure. The Gini Index is a measure of impurity for each one of the leaves. And then we'll have to do a weighted impurity. That should be in a slide to come here in a moment. But Gini Index is going to show us how impure the partitions are. So when we look at a partition down here, let's go down to like this partition right here. Can anyone calculate the Gini Index of that partition? Jay, 100,000 points. Can anyone calculate the Gini Index of that partition right there? And I wish there was, yeah, we can do it still. But you should be able to pretty easily calculate the Gini Index of that partition. That'd be a good test question too, because theoretically it's very easy. What is the Gini Index of that right there, that partition? We can do the Gini of a split, or figure out how it would do the splits here later on. But what is the Gini Index of that? Well, Gini Index, for those listening, is a measure of impurity. So the Gini Index of that partition, which is a leaf, yep, and I'm using those interchangeably right now, like that is just a partition or a leaf in there. The Gini Index is a measure of impurity. So what is the measure of impurity for that leaf right there? What is the measure of impurity for that leaf? Any idea? How impure is it? 0, Clay, 100,000 points, you're right, 0. That has no impurity, it's 100% pure, so the Gini Index would be 0. The entropy would also be 0. Entropy is just another way of measuring impurity, so the Gini Index tells us how pure each of the partitions are, and we can use it to talk about the split and figure out how to split. So we'll be seeing that in a little later here in more slides. But the Gini Index right there is 0. It's a measure of impurity, and when it's higher, they're more impure. So you can see the top example is a high Gini Index indicating, oh, that's entropy. The top example is a higher Gini Index indicating more impurity. The lower example is a lower Gini Index indicating that it is more pure. Like there's more conforming to the majority level. As in these 27 are higher than the 1/3, 1/3, 1/3. We have more confirmation to the conformity to the majority level. Great questions right there. And here is sums of squared error. Sums of squared error is just how much we miss by. Now, if you'll notice, we get a total sums of squared error right here, looking at how we do as a whole. So how do we calculate the sums of squared error? We take the observation, subtract it from the mean of that leaf, and then we square it, and then we add it together. So it's the sums of squared errors. Please notice, we take literally the error right here. What do we do to that error? We square that error. And then what do we do to the squared error? We sum it. So we do the sum of the squared error. What does that mean in my previous example? Remember, we were talking about people's ages. And so if you wanted to figure out the sums of squared error, you could go here and say for this leaf, we have people who are 19, 20, and 21. Now the sums of squared error would be, find the mean of the leaf, which this right here is y bar. So that is y bar, it's the mean of the leaf. And then we go here and we go 19 minus 20, and we square that, equals 1. 20 minus 20 squared equals 0. And then 21 minus 20 squared equals 1. So the sums of squared error for this would equal, oh, no, went too quick there, would equal 2. That is how sums of squared error is calculated. Always try to do small examples like this to make sure you understand it conceptually. Does everyone understand how I'm doing this conceptual sums of squared error right here? You have to do the, let's write the notation above it. You have to do y minus y bar squared, minus y bar squared. The sum of the squared error, and it's the error from the mean, the sum of the squared error from the mean. So that's all we're doing right here, and we're just adding together each of the leaves to look at the sums of the squared errors. So we can add them together. We can add together the sums of the squared errors. You'll see examples right here. It's a little more complicated than mine, but all we're doing is we're looking at if we were to make a partition right here on 2.45. So you would have this being a group. We're partitioning on the X. So you could partition this into one group and the other side into one group. What would be the mean of the left group? The mean of the left group for 100,000 points, the Y values on the left have a mean of what? What would we predict for all those Y values on the left? What would we predict? 100,000 points. What would we predict for all the Y values on the left? Close. Well, remember the Y values. 100,000 still will. The Y values, not the X's. So we're splitting based on the X's. Remember, the X's explain, and then the Y's we're going to make the prediction. So what would we predict for all the Y values? 2.5, Ali, nice answer, 100,000 points. And you notice that is right down here. That 2.5 is right here, and that 2.5 is here. If you're wondering what the mean of this is, well, that's where we did this, and we added them all up together. So you'll notice that we simply have the mean of the right side right there. That is the mean of the right side. Now we can do another partition another way, and we could split on X greater than this, and then you would get this. What is the mean of that side? Remember, it's Y minus Y bars, so you can look down here, and here's where we're doing 4 minus the mean of that group. So 4 minus the mean of that group. I do not know why my mouse does that every 10 seconds. But the mean of that group is being done right there. That is 4 minus the mean of the Y of that rightmost group. And then we would choose the way we would split based on the sums of squared error. So we would actually split the first method because the sums of squared error is smaller. All this key, important stuff right here. So here I was talking about the last bit of notes on Gini and choosing out which split to do. This is a very, 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 very important slide. So what you have right here is we have that we're basically doing a weighted split. So when you do your splitting, imagine this. How pure would a leaf be of one person? What would be the Gini index of one person in a leaf? Every Gini index of one person in a leaf would have to have a Gini index of this. And it's categorical because I'm talking about Gini index or entropy, either one. But every Gini index with one person in there or one observation must be equal to 0. Aaron, you're right, 100,000 points. It'd be equal to 0, Joe also, because we'd predict them accurately. But think about this. You're weighting it. You have to do a weighted, this is like a weighted average right here. All you're doing is doing how many people times their impurity, and then you're adding together the total. Does everyone see this is a weighted average for the split? So when we look at the impurity of a split, the splits, it's not always going to choose like, oh, this is perfectly pure if we put one person here, and this is how the tree decides where to split. It's going to do it in like a weighted way where it's better to kind of do a closer to 50-50 split that gets things divided up really well than to put one person all by themselves and be like, that person's perfectly classified, but this is still very impure. So remember, this is a weighted average right here. And we've already alluded to how to do the sums of squared error part of it, because the sums of squared error is just adding together all the partitions. So you'll just add together the error in this partition and the error in this partition to see how well it's doing. So the top one is a weighted average, and the lower one is just adding together two sums of squared errors to see how a partition does. Does this all make sense? This slide's usually one that people have me review. Just like, how do I find again the impurity of a split? We have the impurity of a, and actually, you know what? We can go back. What is the impurity? That'd be really hard to calculate. This is a very easy calculation here. What is the impurity of this split right here? What is the impurity of that split right here? This split, when it splits, what's the impurity of the split? So don't overthink it. Just remember, you have to look at how the split does. Don't look at the values right here, because the impurity of this split, when this splits, is going to be vastly different. That one's a fun calculation. But the impurity of this one when it splits is what? What is the impurity of that split right there when it splits down below that split, which I currently have highlighted? So the split that we get right here has an impurity of what? What you have to do is you have to look at the impurity of... nope, 100,000 points still. You have to look at the impurity of leaf 1. The impurity of leaf 1 is 0. And you have to look at the impurity of leaf 2 is 0. Then you have to multiply 0 by 19, multiply 0 by 28. That's 0 and 0. And then you have to divide that by how many there are. Yep, 0 again. Yep, because it's perfectly pure. And just think about what you're saying here. It's always about the context. You're saying this split leads to an impurity of this. And remember, it's a weighted thing. So the top one, yep, so what we have right here, I'll write out the equation. So you have to do on top, you have to do n times, I want to use the black pen right here. And thank you for all the questions, Ivy, 100,000 points. Anytime you want me to do something, so I'm going to write it as Gini Index. So this is N1 Gini Index, N1 Gini Index of 1. And then we go here and we do plus N2 Gini Index of 2. And then we go here and we do N1 plus N2. Yeah, it shouldn't be multiply. I'm just thinking through it logically, double check before I'm always afraid I'm going to say one thing wrong and the whole world will go crazy. Everyone just loses their minds. So, where's that note? Past it. There we go. Yeah, it's plus. It doesn't make sense to multiply them because we're not doing probabilities of independent events, so we would not multiply them. So in this example up above, there was something like 19 observations. This is the amount of observations in the first group. I think 27 were in the second group. The impurity of the first split is 0. The impurity of the second split is 0. And so we multiply that by 0. That's the impurity of those. And then we go right here and we get 19 plus 27. So we would need to know the impurity of each one. So it can be a longer calculation thing. But if you're stuck on any of these, like if they're on the homework, please ask. But this one was nice and easy because the impurities for these were 0. How did I know the impurities for these were 0? Let's take a look at the notes again and just look at the impurity of 0. So there's the impurity right there, which is calculated via Gini Index. Or you could do entropy if you want. The impurity on the bottom one, it's 28 technically. This one, I can't erase for some reason. Or maybe I can. I don't see the eraser. The leftmost leaf down there has an impurity of 0 because they're all black dots. The rightmost highlighted leaf has an impurity of 0 because they're all white triangles. So you'll notice that both of them are completely pure, so their impurity is 0. Does that make sense? That's how I calculated the impurity of 0. And just for anyone watching in the future, I wrote 27. It is technically 28. That is the amount of observations inside of that partition down there. Does that make sense right there, Ivy? The Gini Index was very easy to calculate. It'd be a little harder if I had to do this for a longer question. I might do that, especially with our Friday like extra times and stuff. I might do a calculation of a Gini Index, or I might make a video of it. So, and please ask, if you want videos of topics, please ask. I've got spare time. Be like, hey, Brian, can you make a video explaining this topic? I'll try to make it quick, and it can be topical videos. And, but yeah, so please ask those questions. Anything you want to know, we will go over. You're welcome, Ivy. Always glad to take all the questions. So everyone following along. So consider some partition a variable, new rule. Yeah. So how do we do the splitting? Okay. So when it comes to doing the splitting, what is our goal with impurity? What do we want with impurity? What do we want with impurity? I can't state this enough. We want impurity to be as low as possible. So when we look at splitting different ways, if we were to split on sold 13, if you notice the way this graphic looks, I'll kind of hover over it. These are all the unique values to have the lowest possible value of impurity. You got it, Aaron, right there, 100,000 points. We want it to be the lowest possible value. And what do we see? If we split right here, then we would get the lowest possible values of impurity. Now, the sums of squared error is going to work the same way, and we might have more variables. But tell me, will this, and I'll have to zoom in on it, will this model choose to split on high school GPA, or will it choose to split on ACT? For the first time it splits, will it split on high school GPA on the left or ACT on the right? Which one will it choose to split on, and why? It'll choose to split on GPA. You're right, Aaron, 100,000 again, because high school GPA, Clay right there. It'll choose to split on GPA because this allows for the lowest sums of squared error. It's going to split high school GPA at about 3.72 or something, wherever this is. Do you notice how ACT has more kind of bounce to it? That's because ACT doesn't have as many unique values. What does this tree do? It literally looks through all the values of X. It goes through every single value of X and says, should I split here? Should I split here? And then it calculates what would happen. So this is why we don't do these things by hand much, is because it's calculating every single sums of squared error on every single variable for every single unique value of that variable. That's amazing. We don't have to do that. We just let it do it and say, okay, here's where we split. This is the best spot to split here. And then it recalculates everything and says, okay, let's look at these. Let's find the best spot to split. And let's see what would lower the sums of squared error the most. Where would we split? So a lot of calculations are happening in the background, just tons of kind of almost simple mathematics, but like thousands or tens or hundreds of thousands of equations are being done for you to figure out where do we split. So the decision made where to split is either done by purity or impurity, if you want to call it that, and then it's also done on sums of squared error, depending on categorical, impurity, sums of squared error, entropy, or quantitative sums. Let me restate that. Categorical variables use impurity, which can be measured by entropy or the Gini Index. Quantitative variables use sums of squared error to figure out how well the model is doing. Would GPA versus ATT have a more pure split? Remember, Aaron, that these ones aren't measures of impurity. These are going to be sums of squared error. So these right here would have more error in the calculation. Splitting on ACT, the right one, very hard to see the text right there. Splitting on, that was totally Nelson, right? Welcome to, we see the one on the right is going to have higher error if we were to make predictions. If we were to use it to make predictions, it would have a higher sums of squared error. And this one here is sums of squared error. This one here is impurity because we're predicting a categorical variable. So categorical variables use impurity. Quantitative variables use sums of squared error. Big concept right there. Great question. Again, the tree and the rules, composed, built in stage. Yeah, I think it's everything I've been saying. We just keep repeating this process. I think we show it right here visually, is we start by just making a split, and we're doing a impurity right here. Where would we go, left or right here? If we split to the left, we will get an impurity reduction, and this is an impurity reduction of 0.042. If we split to the right, we'd get an impurity reduction of 0.048. So which way would we split right now? Any ideas on which way we would split? Any ideas? Any ideas? To the right, it's underlined. And this one in the middle would lead to the biggest impurity reduction, 100,000 points right there. So we'd split right there. And we just keep redoing this. If you notice, it just keeps recalculating the impurity reductions based on all these, to all 100,000 points. So it just keeps splitting and splitting based on where. And we'd split on leaf 2 right here because it calculates that's the biggest impurity reduction. Now, this is where we get to things like CP. I think we're almost to that. But and we might just be able to mention that just with tons of splits. Yeah, it goes really fast. Yeah, it can get complex. Can you build a tree till the newest tree doesn't enough? Here we go. Yeah, because we're literally to the idea of CP. Yep, exactly. This will be our last topic for today. So stay focused here as we do our last topic, and then we'll finish this up and we'll start lab. And remember, I do post the videos for the lab, and the answers are pretty much there. So it's a lot of practice. Make sure you're practicing it. How do we know when to split the tree enough? If you notice, the impurity reduction right here is getting water each time. The impurity reduction is getting water each time. The impurity reduction is getting water and water and water and water and water each time. You keep doing this, and each time your reduction in impurity is getting water. It's getting smaller because you're trying to like make the tree work really hard to get the work done. You're like, okay, you got to keep splitting. You got to keep splitting. And it's like, I can only reduce it by this much this time. I can only reduce it by this much this time. So it's going to have a harder time splitting the tree apart each time. So when we do this right here, we need to see how much do we build the tree. We can put in a few tuning parameters that we would want at least so many individuals in the tree. So we can tell it split until you cannot get this amount of a decrease, or we would tell it don't have, like you can only have this many people in a leaf. So we've got 2 tuning parameters, keynote to take. 1, how much of a reduction in purity do we want? First bullet point. 2, what is the minimum amount of individuals we will let be in a leaf? Like, do we want 1 person in a leaf? That might be overfit. So you'll see right here, we've got the fraction decrease. This is how it's done in sums of squared error. We have the sums of squared error before. We have the sums of squared error after, and we compare that. Because imagine before the sums of squared error was 2 and now it's 1. Well, that would be awesome. So this is the way we can calculate the CP right here to see the fraction decrease in the sums of squared error. And I just want to get to a few notes on CP because it's such a big important concept. The optimum value of CP, like what is the correct amount to split it? Well, we don't know. We're going to do many different things. We're going to tune this. Here's 2 big notes I want you to have. We're going to go for like 1 more minute. But CP controls how large the tree grows. So a CP controls how large the tree grows. I want you to think about this. If you were to put CP at 0.000000001, you're telling it to split the tree, you only need to achieve that much of a decrease. Would the tree split a lot more or a lot less? If you asked for a CP of 0.001, would the tree get huge or be very tiny? So remember, you're saying you have to achieve a decrease of this to at least this to split the tree. If you said 0.001, the tree would get a lot. And you'll see that right here, we have smaller values, while smaller values of CP lead to a larger tree. Does everyone see this? Smaller values of CP, because you're saying you only need this, a lot less. So it would be smaller CPs lead to larger trees. Because what you're saying is to split the tree, you only need this return. Does everyone understand how to interpret CP? CP means to split the tree, you need to get at least this return. So watch as we go back to our example that while we do this, the return we're getting, like the improvement, is less and less each time. So if I put my CP to 0.05, would this tree split again? Well, I'd have to go back here. If I put my CP to 0.04, would this tree split? If my CP is at 0.04, would this tree split? Yes or no? Last example of the day. 1 more minute. If you have to leave, you have to leave. Don't worry. Would this tree split with a CP of 0.04? Yes or no? Would this tree split with a CP of 0.04? Any ideas in the chat? 100,000 points, who knows? Would this tree split with a CP of 0.4? The answer is yes, because it will split, because we do get at least a return of 0.4. Would this tree split with 0.4 CP? Would this tree split with 0.4 CP? The answer is, once again, yes, because we do get a return of at least 0.04. And hopefully I'm saying 0.04, not 0.4. Would this tree split with 0.04? No, because we do not get a return of at least 0.4. This tree right here, if we have the CP set to 0.05, we'd actually get the what model? Million point question of the day. If we have the tree split to 0.05 CP, we'd actually get the what model? Million point question. Who's going to get the last question of the day? We'll maybe do last question, million point question most classes. Who knows it? If this tree was set to 0.05, naive Caleb, nice job. You'd get the naive. Caleb was first. Caleb was right. Everyone else gets 100,000. Caleb, great job. Because the tree would not split. Does that make sense? The tree's going to be like, can't do it. Can't split. Don't get the reduction you want. So does everyone see, what did I do? I made the CP higher and the tree split less. If you make the CP lower, the tree will split more because it's like, oh, I only need this return. Split, 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 split. But if you make the CP really high, it's like, I can't achieve that. I'm not going to split. Does everyone kind of understand what's going on here with CP? It works the same for sums of squared error, that if you put a high CP for sums of squared error, the tree's like, I need this big return. And it probably can't split as much. But if you put it super low, the tree's like, I can split all I want because I only need this tiny return. Who thinks they understand CP pretty well? It's what controls how much the tree splits. We get to control it. We get to say, let's make a really large tree. Let's put CP to be really tiny. So they're inversely related. Small CP, larger tree. Larger CP, smaller tree. Hopefully everyone understands that. That's the last concept I want to teach today. We've only got, I know there's a lot of slides after this. There's a lot of review slides in here, and there's also like a few concepts. But once again, great class today. Great work. Any other last questions? I'll be here for like 3 more minutes before I start switching over to the other class. Any other last questions? Lots of great examples today and lots of great questions. Thank you so much, everybody. You guys still having fun? I hope. Who is still here? Game of Thrones outro. I actually had, maybe I'll bring it back. I used to sit on the throne. You're welcome, Caleb. How will office hours work? I'm going to start posting the times. But anytime you see me live on YouTube, you can join in, Ivy. So subscribe to the YouTube channel if you want. Easiest way to find out when I'm live. You're welcome, everyone. So find out, like, I'm going to post it probably later today. I've just been getting everything situated and I got a green screen finally. Yeah, not for this week yet, but lab last week was posted on Friday. So the lab overview for last week's lab is posted, and a lot of people are doing great on it. There's one small error. It's with the, you'll see it. I should send out an email about it. Probably should. But yep, Julia, great to see you too. And I think that's got it for everybody. So hopefully, ask questions if you got it. Got like 2 more minutes, and then hop over to the other stream. Playback error occurred. You're welcome, Aaron. Yeah, we had a good time doing lab. Nice fun time working the lab out. So come to labs on Friday. We're gonna do them in class still, but then I'm also gonna hold like a lab on Friday where we just go through questions and work assignments or stuff. So we'll try to do as much work as we can online. And so and also obviously I'll start posting office hours and I'll start appearing more regularly at regular times. It's just been a lot of emails, a lot of like 100 emails today. 100 emails each day can kind of be an understatement. So, but I appreciate it. I want everyone to keep emailing me. If I email back like within 2 minutes, that probably means I'm getting a lot of emails because I'll just be like email, and I'll keep going through them. So I think that's got it. Great seeing everyone. I'm going to go ahead and end the stream right here. We need to get some new intros. I know, and I appreciate you guys so much. Keep asking questions. Keep working hard. You know you can always get a hold of me. You can always email. You can always find me on a live stream. Hop in the chat. Ask questions. I'm here for you guys, and you guys are doing great. I appreciate all the hard work. You're welcome, Zach. I will see everybody later. Does the button not work? Oh no! I got to redo my thing.